Welcome to lesson 9 in power system analysis. In this lesson we will discuss about transmission line steady state operation. Well, when we talk about the steady state operation on transmission line, what we really mean is how the line is going to perform when we want to transmit certain amount of power through it. So, here what we will do is we will discuss and derive the relationship between the voltage, currents and the power which is transmitted over the transmission line. In the earlier lessons we had derived the models for the transmission line. Mostly we had used the ABCD parameter model and the pi equivalent circuit model. Here we will try to take help of the ABCD model and develop the power transfer relationship on the transmission line using this ABCD parameters. First we will consider 2 bus power system, the simplest one, a generating station supplying power to a load through a transmission line. The system as shown in this figure has this generating station which is connected to a bus bar. The voltage of this bus bar is Vs, because we call this bus as the sending end bus. The current flowing from the generator into this bus is Is, and then this bus sending end bus is connected to the receiving end bus at which the loads are connected, this by means of a transmission line. The transmission line, as we have said earlier, is characterized by the ABCD parameters. So, for this system Vr is the voltage at the receiving end, and normally what we assume is that we take this receiving end voltage phase angle as 0 degrees, whereas the sending end voltage phase angle as angle delta. The sending end power, the complex power at the sending end, Ss is equal to Ps plus jQs, where Ps is the real power and Qs is the reactive power at the sending end. Similarly, Sr is the complex power at the receiving end, where Pr is the real power at the receiving end and Qr is the reactive power at the receiving end. Now, we will try to develop the power flow relationship for this system. We have already developed the relationship using the ABCD parameters for the transmission line as VSIS is equal to ABCD VRIR, that is the sending end voltage and current in terms of receiving end voltage and current with ABCD parameters for the transmission line. If we solve these equations, then in terms of the sending end and receiving end currents, then we will get the receiving end current IR is equal to 1 by B Vs minus A by B Vr, and Is is equal to D by B Vs minus 1 by B Vr. We have already seen that A is equal to D, therefore, we will replace this D by A and we have Is is equal to A by B into Vs minus 1 by B into Vr. So, once we have found out these currents, the receiving end and sending end currents, we can write down the relationship for power. Now, here as I said earlier, the receiving end voltage Vr, we are assuming it to have a magnitude Vr and the angle 0, that is, we are making this receiving end voltage as a reference phasor, and Vs is equal to magnitude of Vs and an angle of delta, which is the angle by which the sending end voltage leads the receiving end voltage. Also we have D is equal to A, and A, since we know is a complex number, we are writing this A as magnitude of A with a phase angle alpha, and B, as we know, is comes out to be equal to Z for a pi equivalent circuit. So, this is also a complex number, and we are writing B as magnitude of B with an angle beta. So, once we substitute these values for Is and Ir, then we have Ir is equal to Vs magnitude of Vs by magnitude of B with an angle delta minus beta, and minus magnitude of A into magnitude of Vr divided by magnitude of B with an angle alpha minus beta. We are just substituting the phasor values for A, B, C, D and Vs, Vr in this relationship. Similarly, we can get the value of Is as A Vs by B, all these magnitudes, with an angle alpha plus delta minus beta minus Vr by B with an angle of minus beta. Now, we will try to find out the conjugates for these currents, because we know that the complex power S is given by V I conjugate. So, we will get the conjugates of these currents as IR conjugate will be equal to Vs by B with an angle beta minus delta. This angle what we had earlier is now replaced by the negative of it when we take the conjugate. So, instead of delta minus beta, we have now beta minus delta here. Similarly, this other term is minus A Vr by B, and the angle instead of alpha minus beta as we had for IR conjugate, this angle becomes beta minus alpha. Similarly, we find out the conjugate for the sending end current Is. This is equal to A Vs by B angle beta minus alpha minus delta. Again, we take the negative of the angle that we had for Is minus Vr by B with an angle beta, because earlier we had here we had Is, here we had an angle of minus beta. Therefore, Is conjugate is given by this relationship, A Vs by B angle beta minus alpha minus delta minus magnitude of Vr by magnitude of V angle beta. So, once we have got these conjugate of the currents at the receiving end and sending end, we can write down the power relations now. The power which is received at the receiving end or received by the load SR is equal to PR plus JQR, where PR is the real power and QR is the reactive power, and this is equal to VR into IR conjugate. And since we have already calculated the value of IR conjugate, for getting the value of SR we need to multiply that relationship by VR. Since we know VR is equal to magnitude of VR and angle 0, so we multiply that relationship by VR with an angle 0, and we get this as VR angle 0 multiplied to Vs by B angle beta minus delta minus A Vr by B angle beta minus alpha. This can be written as Vs into Vr, magnitude of Vs into Vr by magnitude of B with an angle beta minus delta minus magnitude of A into magnitude of Vr square divided by B with an angle beta minus alpha. Similarly, the power from the sending end, that is the power which is sent by the generator, is Ss, and that is equal to Ps plus Jqs, the real power Ps from the generator and the reactive power Qs from the generator side. This is equal to Vs into Is conjugate. So, again what we had already calculated, this Is conjugate, we multiplied by Vs, and Vs we know is magnitude Vs with an angle delta. So, we multiply this, then we get Vs angle delta multiplied by Is, which is equal to A magnitude of A into magnitude of Vs divided by magnitude of V with an angle beta minus alpha minus delta minus of magnitude of VR divided by magnitude of B with an angle beta, which when we simplify this whole thing turns out to be magnitude of A into magnitude of Vs square divided by magnitude of B with an angle beta minus alpha, because this delta which is plus delta will cancel out with this minus delta, minus Vr magnitude of Vr into magnitude of Vs divided by magnitude of B into angle beta plus alpha. Now, if we take out the real and reactive parts from this complex powers SR and SS, that is, we take out the real and reactive real and imaginary part of these equations, these complex equations, then we will get the real power and reactive power. So, PR will come out to be Vs into Vr by B cos of beta minus delta minus A into Vr square by B into cos of beta minus alpha, and Qr, the reactive power at the receiving end, will be equal to Vs into Vr by B into sin beta minus delta minus A into Vr square by B sin beta minus alpha. Similarly, the real power at the sending end will become equal to Ps, and Ps is equal to A Vs square by B into cos beta minus alpha minus Vr into Vs by B cos beta plus delta, and Qs, the reactive power at the sending end, will be given by A into Vs square by B sin beta minus alpha minus Vr into Vs by B into sin beta plus delta. Now, these quantities PR, QR, PS, QS are giving us the relationship for real and reactive power supplied at the sending end and received at the receiving end. Now, from this equation, PR equation, we can see that for a given system voltage level, Vs and Vr will be very near to the system voltage and they do not change much. That is, if you have a 400 kV system or a 220 kV system, these values will be very near to 400 kV or 220 kV, whereas this beta is basically the angle of the impedance of the transmission line, that is, if we are using a pi equivalent circuit, or these parameters beta, alpha, all these are transmission line parameters, and once the transmission line is already there, then these parameters are fixed. So, we see for any given transmission line with the system voltage, for a given system voltage, we have only one parameter, this parameter delta, which can be varied, which is the power angle or the voltage phase angle at the sending end, and we can get a maximum power which can be transmitted or which can be received by the load on this transmission line for a given system voltage level, that will be equal to PR max. This is equal to Vs Vr by B, and when we make this beta equal to delta, then this cos beta minus delta is equal to 1, and this will be the maximum value, and that is what we get here, Vs Vr by B minus a VR square by b into cos beta minus alpha, and corresponding to this maximum power that will be flowing, we have the reactive power at the receiving end given by minus a VR square by b into sin beta minus alpha. Now, what we see from here is that if the real power is maximum, then the corresponding reactive power received at the load end has to be negative, means the power has to be transmitted for a leading power factor load. That is, the load power has to be leading for this condition. Now, in order to understand this phenomena of what actually is happening on the transmission line and get a better concept of this power flow and how it gets affected, we would like to make our system much more simpler. So, let us first make this line as a short line, and for short line we know A is equal to D is equal to 1 angle 0 and B is equal to Z angle theta. Z is the series impedance of the line and theta is the angle of the impedance. Then substituting these values, we get PR is equal to Vs VR by B, B is now Z. So, we have got Vs VR by Z cos of beta minus delta, beta is now theta. So, theta minus delta minus VR square, because A is now 1, VR square by Z into cos beta was the term. So, here it is cos theta. Similarly, we can write QR is equal to Vs VR by Z sin theta minus delta minus VR square by Z sin theta. For the sending end powers, we can write the similar relations for the short line. Ps is equal to Vs square by Z cos theta minus Vs VR by Z cos theta plus delta, and Qs, the reactive power at the sending end, will be equal to Vs square by Z sin theta minus Vs VR by Z sin theta plus delta. Now, in most cases for the transmission line, the resistance is much smaller compared to its reactance, and therefore, we can say that magnitude of Z is very much equal to the magnitude of X, the reactance, because we know Z magnitude of Z is equal to square root of R square plus X square. Since R is much smaller, most of the transmission line, overhead transmission line, the value of R will be either 1/3 or even less than that of the reactance of the line, and therefore, we can say the magnitude of Z is approximately equal to the magnitude of X, and we also can say that the angle theta in this case will be very close to 90 degree. That is, we are saying that the line is purely reactive in this case, because resistance is much smaller and can be neglected. Therefore, substituting these values, that is Z is equal to X and theta is equal to 90 degrees, we get PR is equal to Vs VR by X into sin delta. This is a very important relationship for power flow on the transmission line. Similarly, we will get QR is equal to Vs VR by X into cos delta minus VR square by X. Now, for power system operation, normally the angle delta is small, and therefore, we can say that cos delta is nearly equal to 1. Therefore, if we substitute this, then we have QR is equal to Vs VR by X, Vs VR by X minus VR square by X, which can be simplified into VR by X into Vs minus Vr. Now, this relationship for QR and this relationship for PR, the real power received at the load end and the reactive power at the load end, is these are very important relation, especially for understanding what is happening. From these relationships we can draw following conclusions, that is, for fixed values of Vs, Vr and X, that is for a given transmission line and given system voltage, the real power depends on angle delta, the phase angle by which Vs leads Vr. This angle delta is called power angle. This is mainly because this is the angle delta which is determining how much power is going to flow on the line. Therefore, we call this as power angle. When delta is equal to 90 degree, P is maximum, that is the maximum power that can be transmitted through this system can be, when this delta is 90 degree, then sin delta is equal to 1, then the maximum power that can be transmitted is Vs Vr by X. So, when delta is equal to 90 degree, P is maximum, that is maximum power that can be transmitted. For system stability consideration, delta is generally kept much smaller than 90 degree. It is normally worked in the range of 20 to 30 degrees only, because any sudden large disturbances can make system unstable if we work very near to 90 degrees. The another inference that we get from this relationship is that power can be transferred over a line even when Vs, magnitude of the sending end voltage, is less than or equal to the receiving end voltage magnitude. Normally, we always assume that the voltage at the sending end must be greater for power to be transferred. This is the case for a DC system. If a power has to be transferred from one end to other end, then the sending end voltage must be larger than the receiving end voltage. But in case of AC transmission system, this is not necessary. The value of the sending end voltage magnitude can be lower than the receiving end voltage magnitude, still real power can be transmitted over this line. It is the phase difference delta between Vs and Vr which determines how much power is going to flow. If delta is positive, that is Vs leads Vr, then the power will be flowing from the sending end to the receiving end. If delta is negative, that is if Vs lags Vr, then the power will be flowing from Vr side to Vs. So, it is this phasor angle which determines the direction of power flow and not the voltage magnitude. This is a very, very important concept in AC transmission. Now, most of the power systems are operated with almost the same voltage magnitude. That is, what we do is, in order to keep our system running properly, we keep the system voltage at most of the buses in the system very nearly equal to the nominal system voltage. So, say for a 220 kV system or a 400 kV system, we would be keeping the voltage magnitudes at most of the buses very near to 220 or 400 kV, because this provides us a much better operating condition for the system. That is, power systems are operated with almost the same voltage magnitude, that is 1 per unit at important buses, by using methods of voltage control. This is what we will talk about later in this lesson. The third inference that we can derive from this relationship is the maximum real power transferred over a line increases with increase in Vs and Vr, that is the sending end and the receiving end voltage. An increase of 100% in Vr and Vs, that is if we double the voltage level of the transmission line, then the power transfer increases to 400%. That is, if the line initially was capable of carrying 100 MVA, now if we double the voltage, it will be able to carry 400. Sorry, if it was able to carry 100 MVA, now if we double the voltage, it will be able to carry 400 MVA. And this is one of the main reasons why we keep going for higher and higher voltage levels when we want to transfer more and more power. Another important inference that we can derive from this expression is the maximum real power depends on reactance X, which is directly proportional to the line inductance. Now, as we have seen, P max is Vs Vr by X. Therefore, if we decrease the value of X, P max will increase. A decrease in inductance increases the line capacity or the power transfer capability of the transmission system. Now, which means we need to decrease the inductance. As we had seen earlier, we can decrease the line inductance by using bundle conductors, because bundle conductors will increase the effective radius of the conductor and therefore reduce the inductance of the transmission line. Reducing the inductance of the transmission line will reduce the reactance and therefore it will increase the power transfer capability or the maximum power that can be transmitted on that line. Another method of reducing the reactance is by connecting a capacitor in series with the line. Now, if we connect a capacitor in series with the line, then the total effective reactance of the line will get reduced, because the reactance of the capacitor will be negative and will be reducing the effective reactance of the total the effective series reactance of the transmission line. This method of connecting a capacitor in series with the line is called a series compensation of the transmission line, and this is generally done in order to increase the power transfer capacity of the transmission line. Because as we had seen in the earlier lesson, most of the time we run our system at much below the thermal limits, mainly because the stability limits are the major problem, and we have to ensure that we run our system properly even when there is certain large disturbance which takes place in the system, like short circuits and tripping of lines or generators. Even when these take place, still the system should run synchronously, and for this we need that delta angle should be much lower than 90 degrees, that is in the range of around 20 to 30 degrees, and that is why unless we reduce the reactance of the transmission system, we cannot transfer large amount of power through that transmission system. Now, as I said, we can reduce by using a series capacitance, that is connecting a capacitance in series with the line. The series capacitors are usually installed at the middle of the line. This is generally done for one simple reason, that if we install them at either the sending end or at the receiving end, then when the loads are low, the voltage values at these ends can go very high because of the large amount of compensation which is available at those ends, whereas if we put them in the middle of the line, the voltage profile generally will be much better. From the reactive power relationship, we derive the following inferences. The reactive power transferred over a line is directly proportional to Vs minus Vr. That is, if we go through this relationship, Qr is equal to Vr by x into Vs minus Vr, that is, Qr is directly proportional to the difference of the voltage magnitude Vs minus Vr. Therefore, we see that the regulation, that is the voltage difference that comes when the line is loaded, is very important, and that governs the reactive power flow on the transmission line. So, reactive power transferred over a line is directly proportional to Vs minus Vr, magnitude of Vs minus magnitude of Vr, that is the voltage drop along the line, and is independent of power angle. That is, in this relationship we do not have any power angle delta coming into picture. This means the voltage drop on the line is due to the transfer of reactive power over the line. That is, it is because of the reactive power which is being transferred over the line that there is a large drop in the voltage. To maintain a good voltage profile, reactive power control is therefore necessary. That is, if we want that the voltage drop is not large, then we have to see that the reactive power transferred over the line is reduced as much as possible. This is done by means of what we call reactive power compensation of transmission lines. So, now we will look into how we control the voltage and so the reactive power flow on the transmission line. Reactive power compensation equipment has following effects. Basically, why we need this compensation? We need this compensation mainly to see that the voltage profile of the line is maintained as near the nominal value as possible. Now, the question comes, why it is so important? Well, if we go at higher and higher voltages, what we have is we need to insulate these lines from ground as well as the insulation between line to line, which means that we need to use insulators, and these insulators will be expensive if we need to provide large amount of safety factor. That is why at extra high voltages of 400 kV and above, the safety factors may not be very large in order to make the transmission system economic, and for this purpose we say that we work these lines or these transmission systems at a level of only around plus minus 5%. That is, the voltage which is allowed to change is up to a level of plus minus 5% from the nominal value, which means that the maximum voltage drop that can be allowed on a transmission system is only of an order of 10%, right, and therefore, it is necessary that we use some control equipment to keep this voltage within these limits, or the voltage drop is not allowed to go beyond this, and if it goes, some compensation equipment has to be there to boost it up and keep the voltage drop within the permissible limits. Now, the reactive power compensation equipment has the following effects. First is reduction in current. When we are reducing the reactive power flow on the transmission line, what we basically mean is the current component of the reactive power flow is also getting reduced, because we know the complex power is P plus j q, and if we and this is equal to V into I conjugate, and therefore, if we reduce Q, then we are reducing S, and we are thereby also reducing I, because V is very near to the nominal voltage. Therefore, if we reduce the reactive power flow on the line, we are also reducing the current. We are also able to maintain the voltage profile within limits if we reduce the reactive power. As we said, if we QR is given by VR by X into Vs minus VR, and this Vs minus VR will be reduced if QR is reduced. Since the current flowing gets reduced, therefore, the losses I square R losses on the transmission line will also get reduced. This is another advantage in having reactive power compensation on the system. Of course, this means that there is going to be reduction in investment in the system per kilowatt of load supplied, for the simple reason that if we are reducing the reactive power, we are reducing the current, and therefore, the transmission line that we are using can be of a smaller diameter as such, which will reduce our investment. Also, all the equipment that we have are rated in terms of their kVA or MVA capacity, that is the volt ampere capacity, not the kilowatt or megawatt or watt capacity. This is because all the equipment has a current rating associated with it, which is basically dependent on the I square R losses that can be dissipated from that equipment, so that the temperature of the windings and other parts of the equipment is maintained within a given limit. Otherwise, the insulation of the equipment will deteriorate very fast, and the machine will go out of order, because it will lead to short circuits. So, by using reactive power compensation, we are reducing the reactive power requirement of the system, and therefore, we are also reducing its kVA requirement, or we are reducing the investment in system per kilowatt of the load supplied. Now, decrease in kVA loading of generators and lines happens because of this, and this decrease helps us, because this decrease in kVA loading relieves the overload condition or releases capacity. Suppose I am running a system to its limit, say I have a 50 MVA generator, and I am running this generator at 50 MVA at 0.8 power factor. Now, that means the load is going to be only 40 kilowatt and the MVA is 50. Now, suppose I increase the power factor to 0.9, then what happens? Keeping the generator capacity or still running this generator at 50 MVA, now I will be able to supply 45 megawatt. That means, this 5 megawatt capacity is now released. So, I can supply more load from the same generator. Therefore, reactive power compensation helps in relieving extra capacity or relieving overload on the equipment, and that is generators, transmission lines, etc. It also helps, as I said, if we increase the power factor, it helps the generator also, because it will have to generate less amount of reactive power, which means that the excitation system will be working with lesser current. We do not have to over excite the generators. Of course, for the consumers, the advantage is there is going to be reduction in their kVA demand charge, because large consumers are charged not only on the basis of the energy they consume, but also on what is their maximum kVA demand, because basically the utility which is supplying to these consumers have to build the transmission system, the transformers have to be installed. All these have to be done on the basis of what is going to be their maximum kVA demand. So, if we have improved the reactive power requirement, then what we have done is we have reduced the kVA requirement, and therefore, the kVA demand charge which is charged by the utility will also get reduced. Now, how do we provide this compensation? Now, there are different ways in which we can provide this compensation, like static compensation, we have rotating compensation, and also we can use transformers for compensation or control of voltage on the transmission line. So, let us take first the static compensation. Well, static compensation basically consists of two ways in which we can do it. One is the shunt compensation and the other is series compensation. Normally, series compensation is done mainly for increasing the transmission capacity of the line, whereas the shunt compensation is used mostly for voltage control, because what it does is it supplies the reactive power to the load, and the reactive power which is demanded by the load is no longer flowing from the sending end to the receiving end, because this is now being supplied locally at the receiving end by the compensating equipment, and thereby releasing capacity on the transmission system. Now, what this shunt compensating equipment consists of? Normally, at the receiving end of the transformer, which will be a 3-winding transformer, the tertiary winding is normally a delta connected winding. So, suppose we have a 400 kV to 220 kV transformer and its tertiary is 11 kV. Now, the compensating equipment is normally connected at the low voltage or the tertiary winding, which is at low voltage, and this equipment consists of basically some capacitors which are permanently connected, some capacitors which are switchable and can be connected or disconnected depending on the demand, and a variable reactor or a saturable reactor, which is the current of which can be controlled by means of thyristor or GTO. So, this is a controllable reactor here. The current flowing through this reactor can be controlled, and therefore, this reactor becomes a variable reactor, and therefore, using the equipment with this capacitors and variable reactor, we can give any value of compensation that we want. Basically, if you see, it is how much capacitance that we are providing that will decide how much compensation we are doing. Normally, when the load is high or during the peak load period, the loads being mostly inductive in nature, it will be the lagging reactive power which will be demanded by the load. So, the loads will be absorbing this lagging reactive power, and therefore, the compensating equipment will have to generate this lagging reactive power to supply it to the load so that the transmission system is relieved of supplying this reactive power. Now, how much is that? That can be found very easily. We have the current flowing in the capacitive shunt capacitors given by Vs by root 3 into Xc, where Xc is the capacitive or the reactance of the capacitors, and Vs is the voltage. Vs is the voltage which is line to line voltage or the system voltage. Now, for a 3-phase system, if we assume these capacitors to be connected in star, then for the 3-phase system we will have the total 3-phase reactive power supplied by these capacitors will be equal to 3 times V by root 3 Xc into, this is Ic, into V, that is per phase voltage or phase to neutral voltage, V by root 3. This comes out to be equal to V square by Xc. Similarly, for this reactor, will be absorbing the reactive power, and that will be given by again this relationship QL is equal to minus V square by XL, right. If we are writing these voltages in kilovolts, then these values will be in terms of megawatts. Now, when the load is low or we have very light load condition, in those conditions what happens is these high voltage transmission line has large amount of charging capacitance. So, there is large amount of charging current which flows through them, which produces large amount of reactive power, and since the load is low, there is not enough absorption of this reactive power. Because of this, what happens is the receiving end voltage goes up, right. Sometimes this voltage can go much higher than that of the sending end. This again is problematic, because we have said earlier that we work within a voltage range of plus minus 5%, and if this voltage goes beyond that, then there is a chance of insulation failure for the insulators on the transmission line, because the voltage will go beyond their rated capacity. This cannot be allowed, and therefore, we under light load conditions we have to absorb the reactive power, and that is done by this reactor. So, we have both absorption of reactive power when we want and generation of reactive power most of the time when the load is low high. We need this part more and this part very less, whereas when the load is very low and the voltage is going higher, then the current through this can be increased and these can be switched off, and again the voltage can be maintained. Now, instead of using static compensators, earlier people were using rotating compensators. These rotating compensators are nothing but synchronous motors which are not mechanically loaded, that is, they run at no load. So, they are designed as synchronous motors running at no load. It is only the excitation that we vary, and varying this excitation we can make these machines either absorb reactive power or generate reactive power. So, a synchronous compensator can supply lagging bars up to its rating, that is up to its designed capacity. So, by over exciting this synchronous machine, we can supply large amount of lagging bars, and by making this machine run under excited, we can absorb the lagging bars. That is, generally these are rated to absorb up to 50% of its rated capacity in terms of megawatts. So, thus a synchronous compensator of a certain rating is equivalent to a static capacitor of that rating, that is, because it can supply lagging wires with that capacity, which a capacitor also can do. Therefore, we can say it is equivalent to a capacitor or a static capacitor of that rating, and since it can absorb up to half of that rating, it is equivalent to that of inductor of half its rating. The advantage of synchronous compensator is that we can very smoothly vary the reactive power absorption or generation by this machine. Another advantage of the synchronous compensator is that it can be overloaded for short periods, whereas this is not possible with static capacitors, because if you try to overload them, they will normally puncture, whereas these synchronous machines have some amount of overload capacity for short periods. Another major advantage for the synchronous compensators is that a drop in voltage causes the synchronous compensator to supply greater wires, because the difference between generated EMF and the terminal voltage will increase, which means the excitation will have to be raised, which helps in arresting the voltage dip. So, it can supply more VAR when the load demands more, even if the voltage drops, and if the voltage drops, by increasing the excitation we can raise the voltage of the terminal. Whereas, in case of static compensation, if we are using static capacitor, if the voltage drops, then what happens is the reactive power generated by these capacitors will also drop. If you can see this relationship, this QC is proportional to or is equal to V square by XC, and if this voltage drops, then QC generated will also drop, which simply means that when we need more reactive power, that is, when the voltage drops, we need more reactive power. The voltage drop occurs mainly because the load is drawing more reactive power. At that time, it is unable to supply larger reactive power. In fact, it reduces its reactive power supply, which will further dip the voltage unless we have other sources of reactive power around. So, in case of static capacitors, a drop in voltage causes a reduction in VAR delivered to the system. That is, it is unable to do or the function for which it is basically used. That is, it can help, but if the voltage goes down, the help also reduces. Another advantage of synchronous compensator is that it is a rotating machine, which means it has large amount of kinetic energy stored in it because of the inertia of the rotating part, and therefore, it helps in making the system more robust and more stable. So, inertia of a synchronous compensator improves system stability and reduces the effect of sudden changes in load, because any sudden jerk is taken up by the larger inertia and the system response is not that great. Static capacitor installations can be distributed in the system. However, small size synchronous compensators are very uneconomical. The main reason of not using synchronous compensators nowadays is synchronous compensators are comparatively much more expensive, as well as they need maintenance, whereas static compensators can be installed at various locations. Almost any substation we can install them, and they do not need any maintenance or personnel to look after them, because they are static equipment. Therefore, the static capacitors can be located near the loads and are more effective. We can use small static compensators as per the requirements and put them very near to the load substations or at the load substations, depending on the load requirement. Especially with the use of power electronic devices, this has become now very easy to do, and therefore, this is what we are putting more and more in the system nowadays. Okay, with this we will stop here. We will talk about some other compensating equipment in the next class, and we will work out some problems on transmission lines, which will make things much more clearer. Thank you. Welcome to lesson 10 on power system analysis. In this lesson, we will be continuing from what we did in lesson 9, that is transmission line steady state operation. In lesson 9, we talked about the power flow equations on transmission line under steady state operating conditions. We also discussed how we can compensate for the reactive power flow on the line and thereby maintain the voltage profile on the line. Now, we will take up another problem. Now, this problem states a 3-phase 132 kV overhead line delivers 60 MVA. Mind it, this is 60 MVA, not megawatt. 60 MVA at 132 kV and power factor 0.8 lagging at its receiving end. That is, VR or V2 is given as 132 kV, and the SR is the MVA value is given as 60 MVA at 0.8 power factor lagging. The constants of the line are given as A is equal to 0.98 with an angle 3 degrees and B is equal to 100 with an angle 75 degrees ohms per phase. Now, we need to find for this system sending end voltage and power angle, B sending end active and reactive power, C the line losses and wars absorbed by the line. We will end today's lesson, and in the next lesson we will review whatever we have learned about the transmission line. So, thank you very much.